the first slide, I've been asked to show the history of observations of the lunar exosphere, and I'm here with Tom Morgan, and so I wanted to start with the lunar phases, the second slide, and just to explain, in our observations, we've defined full moon as phase 0, but I noticed in the Selene observations, they defined new moon as phase 0. And so just to be clear what we're looking at, okay? So the next slide, the first evidence of filling in of the lunar absorption lines. Potter and Morgan were actually looking at to define the solar spectrum by looking at the reflected solar spectrum from the lunar surface. And they were trying to figure out why some of the lines seem to be filled in. And they first suggested that the filling in of the Fraunhofer lines in the reflected solar spectrum was due to inelastic scattering of moonlight on both the lunar and Mercurian surfaces. And this was known as the ring effect or Brion scattering. But when they showed this at the American Astronomical Society meeting, Andrew Young said that couldn't be right because there was too much filling in. So they went to McDonald Observatory and observed at high resolution. And that's when they saw the emission line. So this is the emission line spectrum. The next slide. You'll see the discovery spectrum of the lunar sodium in this lunar exosphere. And the vertical axis is distance away from the lunar surface, and the horizontal axis is wavelength. And this resolution is only 5.4 milliangstroms per pixel. So this is very high resolution. And they deduced a column abundance of sodium of 8 times 10 to the 8 per square centimeter. And they also observed potassium. And they got 1.4 times 10 to the 8 per square centimeter. And they implied that the source was impact vaporization. So the next slide just shows a couple of observations of the emission lines. And you'll see on the left is what you would see 600 kilometers above the lunar limb. And you'll notice that far away, you don't see the reflected solar spectrum from the surface like you do on the right. On the right, you see the emission lines, but you also see the reflected solar spectrum. So the picture of the moon's atmosphere, I'm not sure, I might have deleted this. Do you see the Brian, Flynn, and Mendillo? Well, they looked at a wide band pass, and I wanted to point out that with the wide band pass filter, you actually get a lot of scattered light in that filter. So in addition to just the sodium, you also see scattered light. Now, here is the G value for sodium D line, and I wanted to point out that what you see in terms of the emission is a function of both the distance of the body from the sun and the radial velocity of both the planetary body and the individual sodium atom. And so it's really important to carefully know what your G value is, which is the photons per square centimeter per second per atom. So this is just to show the key factors in determining the lunar atmospheric distribution, and you'll know that atmospheric density at the surface often increases with decreasing temperature, which means the atoms condense or pile up on the surface at night. And you'll see that later on in some of the observations. So the lunar exosphere is transient, but it's quite different for different elements. And I'm going to show how the individual elements behave and what the lifetimes of the particles are, which might be, for instance, photoionization or impact vaporization. A lot of different factors go into the lifetime of the particles in the atmosphere. In order to model the exosphere, then you need to take into account both the sources and sinks and how they vary between different species. So they do vary quite a bit among the different species. Now, one of the first papers about the lunar exosphere was Hodges, Hoffman, and Johnson in 1974. And you can see from the summary that they gave upper limits for hydrogen, both atomic hydrogen and molecular hydrogen, but they did give values for helium, neon, and the two isotopes of argon. Now, argon-40 is from the solar wind, and no, argon-40 is radiogenic, and argon-36 is for the solar wind. And I want you to look particularly at neon. Now, they gave a column abundance of 10 to the 5 for neon. So then in 2015, Mehdi Bina from LADI gave a column of 3.5 times 10 to the 4. And then in 2019, we did a reanalysis of the LACE data, the same data that Hodges used, and we got another order of magnitude less. And the reason is because these are all mass spectrometer observations, and neon 20 is contaminated by fluorine, and that was our argument for reducing the column abundance. But this has implications beyond just the amount. It has implications for the lifetime of neon. Because Mehdi Bina claimed that the lifetime of neon was the photoionization lifetime. But if there's an order of magnitude less, then the lifetime of neon in the atmosphere has to be 4.5 days, which would imply that there are other loss processes for neon. And so this, as of now, is still an open question. What are the loss processes for neon? So argon is a radiogenic product of potassium, and it, of course, comes from the deep interior. And geologists are, of course, very interested in what the deep interior is. And by observing argon in the atmosphere, you get a handle on how much potassium there is in the deep interior. This is from the Apollo 17 mass spectrometer data. LACE was the lunar atmospheric composition experiment, and they proposed that the elements carbon, nitrogen, and argon came from solar wind. And of course, this is argon-36 from the solar wind, not argon-40. What do we know about the source of argon-40? Well, it's correlated with moonquakes, and you can see this is, I believe, also from LACE data, and the source is in the bars here, and you can see that every time there's a moonquake, then there's a little bump up in the argon. Okay, yeah, I mean, I already talked about this. It's just that for Monte Carlo modeling, the different processes like photoionization loss, micrometeoritic source, and so forth, they and the lifetimes of the atoms in the exosphere, they're all different for different species. And especially radiation pressure is quite different for the different species. But why don't we go to the next slide? Okay, yeah, this is, I was talking about this, so I must have been ahead. Yeah, for the lunar atmosphere that was published by Hodges, Hoffman, and Johnson, I was just pointing out that for neon 20, they got 10 to the 5th, and per square centimeter. And so the next slide, you know, you fast forward to Laddie, then I got 3.5 times 10 to the 4 per square centimeter. And these are pre-sunrise numbers because the neon, like argon, it condenses at night and then starts to evaporate just before sunrise. But then in 2019, I published another order of magnitude less, and we claimed that the mass 20 is contaminated with fluorine. And that's why we claim that there's less neon than the other two. So the next slide shows how we fit with a model, the neon, to show how it varies during the nighttime. And these are surface number densities because the lace mass spectrometer was sitting on the surface. And so the neon piles up at night on the surface. So, of course, the atmosphere is condensing onto the surface and the atoms are piling up on the surface. But the number density that we got is consistent with a lifetime of neon in the atmosphere of only 4.5 days. Now, the lifetime that Mehdi Bennett claimed was 100 days, and that is the photoionization lifetime of neon. So if our number is correct, then there are other sinks for neon, which might be micrometeoritic vaporization or something else like piling up at cold traps at the poles. But anyway, right now there's a discrepancy in the numbers. Okay, next slide. Okay, so the Apollo 17, this was lace. They also measured argon, and argon has the sunrise is to the left, and you can see at night. Then argon is really interesting because it condenses at night and it actually diffuses into the regolith, so it almost like disappears. And then pre-sunrise, it starts evaporating, and you see this huge surge in the atmosphere. And then during the day, the argon hops around over the day side, but then it starts condensing immediately on the surface at night. So go to the next slide. Oh, I think I already talked to this before, but argon 40 comes from the deep interior because it's a radiogenic product of potassium 40. And so you can see there are periodic moonquakes, and every time there's a moonquake, you get a surge of argon into the atmosphere. So next slide. Okay, so Cesare Grava did a lot of modeling on the argon, and you can see Right at sunrise here, which is 90 degrees in this longitude, you get a surge of argon, and then it, it hops around the surface and it condenses at night. So next slide. Okay, so the black line and the pink and the gray lines, they were all taken the same year, 73. And the reason, the behavior during a lunation is the same, but the amount in the atmosphere is different because the sources are sporadic. They're caused by these moonquakes. And so even though the amount in the atmosphere is different, the behavior is the same. The argon will condense at night and evaporate at dawn. So next slide. This is the same slide. Go forward again. Okay, so you can see immediately from the bottom panel there is potassium. The creep soil is potassium rare earth element soil, and every time Laddie was measuring above this creep soil, there was an enhancement in the argon, which you can see is sort of the aqua color blip there. But other than that, if you look at the same place, pre-dawn is always more or less the same, and dawn is always enhanced. But then the actual number, might be correlated with either whether there was a moonquake or whether you're above this creep soil. Okay, next slide. So Cesare actually modeled what it would look like if you had a sudden enhancement of argon at a particular time and place, which is the top slide on the left. You see this big red spot, and that is a surge of argon, and he modeled where it would go and how it would evolve over time. And so at first it's a little bit blotchy, and then it diffuses out, and then he has many more slides that show that the argon diffuses until you get the normal pattern that we saw before. Okay, next slide. Okay, what this is showing is how they determine how much of the argon is due to argon 40 and how much is due to argon 36 by doing a best fit. Inside the magnetotail is where you don't see any species derived from the solar wind. And so by looking outside the solar wind and inside, you can determine which part of the argon is due to solar wind, which is argon 36. And the argon 36 is about 7% and sometimes a bit more of the total. Oh wait, this is a helium source. But helium and argon are similar because you have helium-4 and helium-3, and of course helium-4 is the dominant, and it's from the solar wind, and helium-3 is radiogenic, so it's similar to argon. Next slide. So what about molecular hydrogen? Well, molecular hydrogen was finally seen, I think, by Lamp, but the Hurley showed that H2 is actually a chemical sputtering. It's caused by the solar wind implantation, the protons, and it's called chemical sputtering because the H2 is derived from a chemical reaction between hydrogen and oxygen bearing soils. which also make water, but you'll hear about that from Parvati. So next slide. Yeah, so this is from Dana Hurley as well, and she looked at the different sources of molecular hydrogen and figured out what amount would be caused by micrometeoroid delivery from the micrometeoroids themselves, and what portion could come from micrometeorite impact vaporization, and what part would come from solar wind delivery. And she claimed that only solar wind delivery would be sufficient. Next slide. And this is just the different branching ratios for the solar wind. Although H2, as we just talked about, is likely chemically sputtered solar wind, of course H plus is definitely reflected solar wind. Neutral hydrogen is definitely reflected solar wind. I'm not sure when this was published, but the OH and H2O, they said it was not definitely tied to the solar wind, but I think more recently it's been shown that there are pathways to derive OH and H2O from the solar wind. But I think that it's still a matter of debate. So next slide. And I think this is basically the same conclusion, that H2 is predominantly from solar wind chemical sputtering. She claims it might be thermal diffusion, but I think the conclusion is that H2 is from chemical sputtering. And depending on what the H2 density is, then it might require between 10 to 50% of the solar wind. Next slide. And there was an L-cross impacted on Cabeus crater in the pole, and they did observe H2, and they claim that H2 is released promptly on impact and was not a product of photodissociation of water. So that is the main conclusion of this particular slide. Next slide. Okay, so now we go to sodium, and then this is how the lunar phase relates to what we're looking at, because on the left are observations from Potter et al. And I believe these were from Kit Peak. And on the right are Selene observations. And you note that Potter's full moon is 0 phase, but Selene full moon is 180. But once you recognize that, then you recognize that these observations are consistent, because at full moon, over on the left is 0, on the right is 180. That's the minimum. Now, the other thing you have to recognize is that these are surface emissions, and so the surface is the least dense at full moon. But if you look, next slide, what is anti-correlated here is the density on the surface is anti-correlated with the scale height on the left. So on the left, you see at full moon, the scale height is greatest, and at 90-degree phase, while the surface density is greatest, the scale height is least. So what that means is that the actual column abundance is not varying as much as you might expect from just looking at surface density alone. So next slide. Okay, so On the left, now you see the same Selene observations, and on the right you see column abundance rather than what I showed before was the scale height. So the column abundance is, these only show mostly afternoon observations, but our morning observations are similar in that we see the maximum column both at the dawn and dusk limbs, which is not the same as what other people have said would be that there was just a dawn enhancement. We see both dawn and dusk limbs being enhanced in column abundance. And the other thing is that previously it was said that the column abundance with latitude follows a cosine or cosine squared. And our observations are actually the solid line, the cosine are the asterisk. And so our column abundance is pretty flat with latitude. And that's because as the density at the surface decreases, the scale height increases. So if you look at the total column, it's not varying that much. Okay, next slide. Okay, so why is that behavior true? Well, oops. If you look, this is a model back from 1995, and this was Smith and Marconi. They did a Monte Carlo, and you can see it most strikingly with potassium is that at dawn and dusk, at the limbs, the scale height is greatest, and that's caused by radiation pressure. It's not caused by a source. But then, next slide, if you look at the Laddie observations of dust, you see that the dust is peaked at either at dawn or slightly morning. So in the waning gibbous, then the dust peaks more mid-morning, and at full moon, the dust peaks at the morning terminator. And so we think that this is also consistent with where we see the peak of the sodium. Next slide. So one thing that we saw was that if you look at the aqua line, the one with the greatest column abundance, that was actually correlated when the moon was in the magnetosheath and the ion flux to the surface was very high, measured by Artemis. So this is the evidence that ion sputtering is important when the moon is in the magnetosheath. Now, we also see that this is waning gibbous, where in the previous slide you saw that the dust was maximum at mid-morning, not exactly at dawn, but at mid-morning. And this is 9:30 a.m. where we have the next highest column. And then the noon is blue and the early afternoon is purple. So we think that this might be evidence that there is impact vaporization following the trend that you saw in Laddie. So next slide. Okay, so I wanted to show these. These are some interesting observations. The Mendillo group actually was looking at sodium in the Earth's metal layer, and this is where the meteor ablation begins in the Earth's atmosphere, and so the meteoritic metals have their peak up here at about 80 kilometers height from the surface of the Earth. And so they were looking at the metal layer in the Earth's atmosphere, and they saw these peaks in sodium, and they said, what are we looking at? And they said, okay, they were looking anti-solar, and they did a model, and they figured out that what they're looking at is the lunar sodium tail. And this is, you know, the column abundance along these solid red lines through the lunar sodium tail. So this is just a really interesting, sort of a serendipitous discovery, which is really interesting. So we started out with a serendipitous observation of the sodium emission, and we end with a serendipitous observation of the lunar sodium tail. So next slide. Okay, so I wanted to point out that there are a couple of upcoming books that are relevant to the lunar exosphere and to the, well, especially the exosphere. New Views of the Moon 2. I believe that it's gone to the publisher. We don't know when it will come out, but it is written. And Surface-Bounded Exospheres and Interactions in the Inner Solar System. This is from the International Space Science Institute in Bern, Switzerland, and these will come out in Space Science Reviews first and then in a book. So I really encourage you, if you're interested in further study, to take a look at these books when they come out. So that's pretty much it.